Hi, I'm Dave Perellis, an engineer at Tektronix. In this video, I'm going to show you some automated oscilloscope measurements that are useful for characterizing digital signals and pulses. I'm going to use a TBS 2000 series scope to introduce you to digital signal measurements like high, low, overshoot, rise, and fall time. I'll cover pulse measurements like pulse counts and delays. I'm using this circuit board as a source for digital signals, and I'm powering it with this power supply. In the previous videos, we learned how to make measurements on analog and power waveforms. Now we'll take a look at digital signals. In textbooks, digital signals switch neatly between discrete amplitude levels. But in reality, this switching isn't so tidy. For this video, I want to look at real digital signals, so I'm connected to the SPI bus on this digital board. We're going to use the clock signal first, which is a series of digital pulse bursts. Let's take this opportunity to get a little practice with pulse width triggering. In the videos on triggering, we said that edge triggering might not be the best alternative for triggering pulses and digital signals. So I'm going to switch to pulse width triggering. I can see that the clock bursts are less than 1 millisecond long, and they're several milliseconds apart. So I'll set the pulse width trigger on a negative pulse that's longer than a few milliseconds. And let's take a closer look at one of these pulses. Let's select some amplitude measurements so that we can see the difference between them. The key amplitude measurements for digital signals are high and low. Amplitude is related to high and low, so I'll turn this one on last. And to help you understand some of the differences between the amplitude measurements, I'm also going to turn on max, min, and peak to peak. Now let's take a look at them. We learned in an earlier video that max and min are the absolute highest and lowest points in the waveform. For digital signals like these, this includes any overshoot or undershoot. The max in this case is 5.3 volts. The min is about minus 100 millivolts. So the peak to peak, which is the difference between those, is close to 6 volts. The high, on the other hand, is about 5 volts, and the low is 0 volts. The difference between those two measurements is called amplitude, and we see that that's running at about 5 volts. Notice that the high measurement at 5 volts is different from the max measurement, which is closer to 6 volts. The big difference between those two measurements is this overshoot right here. We can use automated measurements to quantify overshoot. I'm going to turn off the min, the low, and the peak-to-peak measurements, because we won't need them. I'm going to turn on the positive overshoot measurement. It's down here at the bottom. You can see that the high is still around 5 volts, as is the amplitude. The positive overshoot is nearly 20%. And that 20% is a percentage of the 5 volt amplitude. So we have about 1 volt overshoot on a 5 volt amplitude gives you 20% overshoot. The negative overshoot measurement uses the same technique, but it's determined relative to the low level. In general, the faster a signal transitions between levels, the more likely it is to overshoot. That brings us to our next measurement, rise time. I'll turn on the rise time measurement. And I'll speed it up a little bit more till we get a nice stable reading. The rise time is the time it takes to transition from 10% of amplitude to 90% of amplitude. In this case, the signal takes around 4 or 5 nanoseconds, close to 5 nanoseconds, to go from a low transition to a high transition. I can verify this by noticing that my horizontal scale is set to about 10 nanoseconds per division, and I've got about half a division that it takes for the signal to transition. Fall time is similar, except that it's the time that it takes to go from 90% down to 10% of amplitude. So far, we've looked at measurements that characterize individual pulses or digital signals and their transitions between logic levels. We might also want to count pulses and check the delays between digital signals. For practice, I'm going to use cursor gating to define the exact measurement area. So I'll position one cursor at the beginning and another cursor at the end of the burst. Counting pulses can be useful for interpreting the position of digital encoders, for example. We'll use it to capture the number of pulses in this burst. Okay, we'll measure the positive pulses. I'll also turn on positive edges and negative edges. We'll count those as well. So you can see that between these cursors, I have 8 positive pulses, 8 rising edges, and 8 falling edges. Now, in this example, it's pretty easy. We can count 1, 2, 3, 4, 5, 6, 7, 8 pulses. But this measurement comes in really handy when you can't count the pulses because there are too many pulses or they're just hard to see. In digital systems, the timing relationships between signals can be absolutely critical. Delay measurements can help you quantify these relationships. I've added a second channel here. It's a device select related to this clock signal. So let's measure the delay between this falling edge of the device select and the first rising edge of the clock burst. So I can go in and select delay falling to rising, and I want to measure from channel 1 to channel 2. You'll notice that there are a number of delay measurements from rising to rising, rising to falling, and falling to falling, so that you can measure almost any combination of delay. I'm going to single shot this so we can take a measurement here. So in this instance, the delay from channel 1, from channel 2 rather, to channel 1 is 20.8 microseconds, roughly. Well, that brings us to the end of this video on digital signal measurements. We've covered almost all the measurements on this scope, so now you should be an expert on automated measurements. But there's still more to learn, so you can look forward to more videos in this XYZ series. Thanks for watching.